uh, if we want to find the j omega crossing using the second method, because we know that when the root Locus cross the j omega axis, S is j omega. So S is not complex anymore, it is pure imaginary, which means that in general S is alpha plus j beta, but here we know that alpha is 0 because it is on the imaginary axis, so it is j omega. So what you do in the second method, so the second method, or the one that I called finding the resonance frequency, so second method, what we do, we set S equal to j omega, and you know that if S is j omega, S squared would be j omega squared, which is minus omega squared, because j squared is minus 1, and then S cubed, which means that you should multiply that by another j omega, it would be minus j omega cubed. So this is what we have. Now we can actually substitute these values to the characteristic equation. Therefore delta S would be, so if I substitute these values to the delta S, it would be equal to minus j omega cubed minus 6 omega squared plus 8 j omega plus k is equal to 0. If we separate the imaginary terms and the real terms, then it would be equal to, so the real terms we have k minus 6 omega squared, and the imaginary terms we have j multiply omega multiply 8 minus omega squared equals 0. So this is what we have. We have this phrase equal to 0. The left side we have a complex number, and the right side we have 0. So when we have a complex number equal to 0, basically the real part and the imaginary part, they should be 0 at the same time. So if you set both to 0, so imaginary part, which is omega multiply 8 minus omega squared equals 0, it will give you omega equals 0 and omega squared equal 8, which gives you omega is equal to square root of 8, and the real part equal 0. It was k minus 6 omega squared, it should be 0. Already we know that omega squared is 8. Okay, let me show you what it means. For imaginary part equals 0, we obtain two different results. One of them is omega is equal to 0, which is actually this point, because omega equals 0, and we know that S is j omega, then it means that S is equal to 0. That's this crossing here, which if you substitute that one to this equation, it will give you k is equal to 0. And if you substitute omega is equal to square root of 8 to this equation, it will give you k is equal to 6 multiply omega squared, which is 8. So 6 multiply 8 is 48. Therefore, it will give you, I'm substituting these values to that equation, it will give you k is equal to 0 for the first one, k is equal to 48 for the second one, which is actually the same result as we obtained. This 48 we obtained, and also this j multiply square root of 8. Okay, here we were talking about S, because of that we had j omega, but here we are looking for omega, which is square root of 8. So that's another way to find that, and we know that this part, actually this is the one that we are looking for. The other one is just this point is the point that we are starting the branch of root Locus. actually this chapter is finished. We talked about our rules. There is another rule that is not mentioned in the book. I will talk about that next week because that's a very useful rule that we can use for designing a controller. But since we are here and we talked everything we need to design a controller using Ziegler-Nichols method, and we have these points, I would like actually to mention that point here. Remember, the j omega axis crossing point that we found can be used to design a PID controller using Ziegler-Nichols second method. Basically, this K we found here, it is Ku, because it is the K that that for that K the pole is pure imaginary, and because of that the step response is pure sinusoidal. So this j omega crossing is actually the point that gives you pure sinusoidal step response. So because of that, this K here is Ku, which is 48, and we found omega u equal to square root of 8, but we know that the period of the step response would be 2 pi divided by omega u. Therefore Tu is 2 pi divided by omega u, which is 2 pi divided by square root of 8. So therefore you have Tu, you have Ku, you can design a Ziegler-Nichols controller. I just wanted to tell you here because the method I talked about in last lecture when we were talking about PID controller, I said that through simulation you can change the gain such that the step response becomes pure sine. So I'm telling that here that actually you can also solve the problem and design a PID controller using Ziegler-Nichols method on paper. It is not only simulation based, or it's not experimental based. Also theoretically you can find the Ku, you can find Tu. How to find Ku and Tu theoretically? Basically you should find the j omega crossing of the root Locus, and to find that as I showed here, we have two methods, using Roth table or using this method that I presented here, that you set S equal j omega and yet you try to find the crossing with the j omega axis. So that was it. So therefore you can also design a Ziegler-Nichols method without simulation, only by theoretically by forming the Roth table or using this method, and then finding Ku, Tu, and then later you can use the table of Ziegler-Nichols to tune the parameters of the controller.